In this video, we're going to talk about position vectors. To do this, let's draw a y versus x graph and then plot some point. This point is going to have an x-coordinate and a y-coordinate. Our position vector is going to start at the origin and then point directly to that position. So this is our position vector. It looks great. Now, because it always starts at the origin and points away, then it's kind of like a radius of a circle. And so we use the letter r to represent our position because the magnitude, or the length of the line, is like a radius. So magnitude is just r without an arrow. And again, that's just the length of the line. And we consider this a radial position. So r is called radial position. We would say where we're at on this circle using our direction, or theta, some angle. And of course, we could write this in the notation r comma theta, or the magnitude in direction, if we want to say where we're located. Another way of writing it would be to say x comma y. So these are two different ways to talk about the vector and this position. Now remember that x and y, they're going to be your x and y coordinates. So you can call this rx if you want, or you can just call it x. I'll just call it x. And the same for y. You could call it ry, but I would just think of it as y. And remember that the x and the y always make a right triangle, so that you can consider the magnitude and direction and the components. So you would find the magnitude r using the Pythagorean theorem, x squared plus y squared. The angle theta using tangent inverse of y over x. The x component would be the magnitude r times cosine theta, and the y component would be r times sine theta. And again, this is all assuming, these three things are assuming that for theta, you are trying to get a unit circle angle, or an angle that's in reference to 0 or the positive x-axis. Okay, let's do some problems with position vectors. Gordon Gekko walks 4 meters right, then 6 meters left. What is his position? Okay, so first they're going to go 1, 2, 3, 4. And then after that, 6 left, which is going to be 1, 2, 3, 4, 5, 6. So here is where the position is. Now I'm going to get rid of these two lines that I drew and think about what the position vector would be. Well, the position vector is going to point right here, and it's going to come out of the origin. Now, this isn't really at an angle, so I can see that this position vector, which again we would call r, this position vector has a magnitude of 1, 2, and that angle that it makes with the positive x-axis is 180 degrees. So we could say 180 degrees. Now, because this is really such a simple idea, you could also just say that his position is 2 meters left. It's pretty simple to kind of verbalize that. All right, let's do another problem. Kenny Powers is on a jet ski. He goes 40 meters north and then 30 meters east. What is his position? Okay, now in this problem, you're first going to go north, which is up, and then east, which is right. So this means you go, let's say, like each of these things represents 10, 20, 30, 40. And then the same this way. Okay. So if you're going to go north 40, you'd be here. And then you'd go east. So east is to the right, 30, which would be there. So this is your position, R. Okay, now to figure out what the magnitude of that position is, I'm going to use the x component, which in this case the x is 30, and the y component, which is 40. And I'm going to use the x and the y component to figure out the magnitude and then also the direction. So let's start with the magnitude. Magnitude is going to be 30 meters squared plus 40 meters squared, which gives me 50. And then the angle is going to be tangent inverse of the y component, which is 40, over the x component, 30. Now that we're using units, you should notice that when you do tangent inverse, the units always cancel out. And that gives you 53.1 degrees. And then I need to think, is this 53.1 degrees correct for the angle I'm looking for? And yes. Remember, if it's in the first quadrant, then a positive angle from tangent inverse is correct. If it's in the fourth quadrant, a negative angle is correct. If it's in the second or the third, you just have to add 180 degrees to what tangent inverse gives you. Okay, so that's the magnitude and direction. So I would say my position vector is 50 meters, comma, 53.1 degrees. Great, let's do another example. PacMan stupidly goes for the cherries. He goes up 4 meters, left 3 meters, down 7 meters, and right 1 meter. What is PacMan's position? Okay, so this actually is a little confusing because there's so many different directions. So you could graph this and sort of just try and think through where PacMan ends up. Or you could also do the component method here and try and keep track of everything. So like this 4 meters up, that would be 0x and plus 4y, which would be 1, 2, 3, 4 right there. Left 3 meters would be a negative 3x and 0y, because you're not going up or down. 1, 2, 3. Down 7 meters would be 0x, and then, let's see, negative 7y? Yeah, because you're going down. So 1, 2, 3, 4, 5, 6, 7. Okay. And then right 1, you'd go positive 1 and 0 for down or up. Okay. So this is our position vector r. And if I figure out what the x and the y coordinate is of these, or of this position, it should be the sum of all the x's and then all of the y's. So let's take a look. The sum of the x's is negative 3 plus 1, so negative 2. And the sum of the y's is 4 plus negative 7, which gives me negative 3. Okay, so is my x negative 2? Yes. Is my y negative 3? 1, 2, 3. Yes. Okay. So my x coordinate, I'm going to get rid of all this. My x coordinate is negative 2, and my y coordinate, or y component, sorry, is negative 3. Okay, so let's start with the magnitude. The magnitude of this vector is going to be the x component squared, so negative 2 squared, which makes it positive, times negative 3 squared, which makes that positive. So the square root of 2 squared plus 3 squared is 3.6. And again, this is a unit, so we would need to say meters. And then the angle. Okay, so let's talk about the angle. Remember, the angle is always in reference to the positive x-axis. So that means here. I could find this internal angle by the tail of the vector at the origin, and then add 180 degrees. Or I can just sort of think, all right, I know that the unit circle angle is going to be this angle right here, which means tangent inverse of my y over my x coordinate. So my y coordinate is negative 3, my x is negative 2. And when I put that in my calculator, I'm going to get second tan, I'll bring this over, second tan -3 divided by -2. And that gives me a positive 56.3 degrees. So I'm going to write that down. Positive 56.3 degrees. But let's think. Is that the correct unit circle angle? Well, like we were just talking about, tangent inverse gives you correct angles in quadrants 1 and quadrants 4. If you're in 2 or 3, you need to add 180 degrees to it. So what happened is we just found this angle right here. That angle is 56.3 degrees, and now we need to add 180 to it to get our correct unit circle angle. So 56.3 plus 180 degrees, which gives me 236.3 degrees. Okay, so that's the angle. Now to write this vector out, we would say magnitude 3.6, comma, angle 236.3 degrees. That is our position vector. Let's do one more problem. Your friend farts, so you walk 2 meters north, then 4.12 meters at 14 degrees to safety. What is your position? Okay, well, for this one, I'm definitely going to do an X and a Y component chart so that I can keep track of everything that's happening. First, you go 2 meters north. So I don't go left or right. There's no X going on. I only go 2 meters north, which is a positive 2. So I'd write 2 for my Y. Okay. Then this 4.12 at 14 degrees to safety. I'm going to write this out, like just kind of sketch it. If I have a little X and Y, 14 degrees is going to look like that. We'll call that theta. And I'm just going to draw some line, 4.12. And you know, I'll write 14 degrees there just to help myself. So what I need to do is I need to take this vector and turn it into components so that I can sort of understand what my new X and Y are going to be. So if I want to find the Y component and the X component, I would use cosine for 14. So this component right here would be 4.12 times cosine of 14 degrees, which is 3.99, so we'll say 4. And this component here would be 4.12 times sine of 14 degrees, which is 0.99 or 1. Okay, so these are the X and the Y coordinates for my second vector that I'm going to use in my little chart. I would say the X is a positive 4 and the Y is a positive 1. Okay, so now I can figure out what these sum to. Right, the sum of 0 plus 4 is 4, and the sum of 2 plus 1 is 3. So this tells me that my new position, these are the X and the Y components of my new position, because I went up 2, and then I went over 4, and up 1. So again, what I'm saying, this is the position vector, R, and my X coordinate is 4, and my new Y coordinate, Y equals, is 2. Okay, so now I can find the magnitude, R, the square root of 4 squared plus 2 squared, which is 4.47, we'll say 4.5. And the angle is going to be tangent inverse of the Y over the X, or 2 over 4. And that's 26.56, we'll say 26.6 degrees. That's theta. Now I used tangent inverse, so I need to think, am I in the first quadrant? Yes, so that is the correct angle. And now I can say that my position is 4.5, I should put meters there, 4.5 meters, comma, 26.6 degrees. And again, we were able to figure out what the two positions are. Like this is almost like your position 1, that's like your position 2. We were able to figure out the x and the y of that second distance that you traveled by making a little right triangle and putting the x and y coordinates in this little box for us so that we could add them and get our new components of our position, which is kind of like the sum of these different lengths that you walked. Okay, great. So these are the basics of position vectors and the different ways to find where you are located after some different displacements that you've walked. Hopefully you are able to see how we can write the magnitude and the direction, and you are super smart, and this video is done.